Hello, hello. I hope you can hear me. This is Interstellar Probe and other Johns Hopkins University Applied Physics Lab missions. I'm Chris Rose. I'm the presenter. I work at Johns Hopkins APL. I'm an avionics engineer, and I hope to share with you a little bit of my enthusiasm and excitement about this mission. Let's see. So this is a little introduction and an agenda. We're going to talk a little bit about other Applied Physics Lab deep space missions that have been conducted or are being conducted. A little bit of history about Interstellar Probe, what that is. I'm going to try to make something like a compelling case for the science that's called for by that mission. Talk a little bit about example instruments and payloads, talk about the mission architecture or different options for that, talk about directions, where we can go, where we can send the spacecraft. We will talk a little bit about the engineering constraints and the trade-offs being considered. And I hope to close a little bit with why we should go. There are a few slides at the very end. If I get through all these slides successfully, talking about other ongoing missions in development at the Applied Physics Lab, I may sacrifice those if I run too long, because this is really the mission I want to talk about. So let's see. Oops. Yeah, so Johns Hopkins has a lot of experience with challenging, long-running, deep space, non-crewed missions. First example is an instrument that went on Voyager 1 and 2. Those were launched in 1977. Voyager now is the most distant human-made object. It's 14 billion miles from our sun, and Voyager 2 is at 11.8. That's 152 astronomical units and 127 astronomical units. An astronomical unit is the mean distance from the Earth to the sun. The one-way light time to send a message to those probes is pretty long. They have crossed the heliopause, which we'll talk about more later, into interstellar space. And particularly they're sending back new and surprising data. And that's one of the things that leads us to consider again how to successfully conduct Interstellar Probe. APL designed, built, and operates the New Horizons NASA spacecraft. It's the first human-made craft to visit the Pluto system. It also visited the first Kuiper Belt object, the first human-made spacecraft to visit the Kuiper Belt object, Arrokoth, not even discovered when the spacecraft was launched. And these two images here, I don't know if you can see my cursor. The first one is an artist's conception of what a Kuiper Belt object might look like. The Kuiper Belt is a set of asteroids and debris from the solar system's formation out beyond the orbit of Pluto. The second image here is what Arrokoth actually turned out to look like. Nothing like what we expected. And let's see. APL designed, built, and operates Parker Solar Probe, a 7-year mission to approach the sun at successively closer radii. It is, when it gets closest to the sun, the fastest human-made object ever. And it continues to set speed records because every 2 orbits, it does a little pass by Venus and gives up some of its kinetic energy, and that brings it into a closer orbit with the sun. The surface of the spacecraft is going to reach 2,500 degrees Fahrenheit. It's going to be 3.83 million miles at its closest approach, something like 5 years from now. It's not a well understood environment. It's a highly energetic environment. And it has this big mystery to be solved because one would expect the heat to be the highest, the closest to the sun. But in fact, there's a region of space outside of the sun that's much hotter than the sun itself. And it's kind of counterintuitive to most folks. And that's one of the mysteries it's trying to solve. So Interstellar Probe right now is a NASA study being conducted by Johns Hopkins Applied Physics Labs and the astrophysical community around it. We are in phase 2 of the study. The technical report that we produce as a result of this will be delivered late this year for input to the next solar and space physics decadal survey. That may or may not be the end of the project. We're hoping that NASA is encouraged by our results to continue with the next phase. So this is not a new thing. NASA was created in 1958, and by 1960 they were already considering an interstellar probe. There were councils from the Academy of Sciences that were making lists of possible missions for the new space administration. There were missions that stayed close to Earth and missions to visit various planets. And then there were these 3 quote unquote special missions. The first one was to go close to the sun. The second one was to go as far away from the sun as possible in a straight line. And the third one was to go out of break the ecliptic, I can never say that, and go over the plane that all the planets are, most of the planets are orbiting in, and look down on the solar system. So let's see if I can make this work. Whoops, I zoomed through. So like I said, the first one was Parker Solar Probe, and it's already launched, and it's in the business making phase of the mission. The third one was Ulysses, which is also launched and has completed its mission. The third one is Interstellar Probe. So there have been a lot of efforts over the years to come to a closer model for how we could actually get Interstellar Probe to work. I'm not going to step through all the history of this, but it's exciting to me that people have worked on this for decades and decades, and we feel like we're finally arriving at a plausible solution. A pragmatic interstellar probe would be a mission through the outer heliosphere to the nearby, quote unquote, very local interstellar medium. That is 1,000 atomic units, 5 light days away from our sun, that would use today's technologies or very near-term future technologies to take the first explicit step into the path of interstellar exploration. This spacecraft would be much faster than the Voyagers, and it would be launched on the SLS or a commercial equivalent. Space Launch System, I think is what that NASA acronym stands for. And this pragmatic interstellar probe could pave the way scientifically, technically, and programmatically for more ambitious future journeys to the outer edge of the solar system and beyond. I'm seeing things pop up in the chat and not reading them all. I hope all these slides are not turning out to be backwards. If the one behind me that you're looking at is backwards, I guess I can live with that. I don't know how to change that now. I'm going to press on. So working with the tools we already have. March 24th, 1163 was the day that the construction of Notre Dame Cathedral in Paris began. And of necessity, it was a multi-generational project. The people who laid down the first floor plans, moved the first cornerstones into place, knew they weren't going to be alive to see the steeple raised, to see the cathedral working. Here are some things they didn't have. Concrete, I-beams, internal combustion engines, construction cranes, architectural software. They didn't have any of that, but they did it anyway. I'm going to come back to this theme later. I feel like there's a really useful parallel here to Interstellar Probe. They are not even kidding about the name. So here's sort of a schematic of the solar system and the near part of the interstellar medium. Let's see. Here is this shows you where Voyager 1 is. When I first came onto Interstellar Probe, I felt like I was pretty okay in my astronomy knowledge. But then I learned about all these different parts of the astrosphere and the interstellar medium, stuff I never heard of before. And I'm still learning. It's exciting to me that there's all this stuff in between here and there, and we don't even understand it all. Oops, I'm pushing the wrong buttons here. But I want you to notice that the scale here is in powers of 10. So for Interstellar Probe to succeed in its nominal mission, it's got to get out here beyond the bow shock, out to the hydrogen wall, into the interstellar medium. 10 to the third is 1,000 astronomical units. One thing that's also not listed on this slide that really excites me is that once you get past about 500 astronomical units, you can turn around and use the sun as a gravitational lens. That's something humans have never had the prospect of doing before. So the science questions here are not new. Like, what is the nature of the nearby interstellar medium? What do the sun and how do the sun and the galaxy affect the dynamics of the heliosphere? What is the structure of the heliosphere? The questions for the corresponding mission and its implementation have always been how far, how fast, when. There's a compelling case for doing this and doing this now. And as the spacecraft moves from our nearest neighborhood around the Earth out of the solar system and into the interstellar medium, it passes through different ranges, but it also passes through different areas where different NASA goals can be addressed. Science goal 1, the heliosphere is a habitable astrosphere. What is the nature of that astrosphere? What is the interaction between that and the interstellar medium? Science goal 2, the origin and evolution of planetary systems. There's a lot of things, we can't tell about our own solar system because we're sort of stuck in the middle of it. If you can get outside of it and look back, there's a lot of things we can learn. And there's a lot we don't know about the Kuiper belt, the debris disk, that would give us clues about the formation of the solar system. And that would tell us about how other stellar systems are formed. Science goal 3 answers big questions about cosmology. By getting out from behind the zodiacal cloud and some of the things that obstruct our really long astronomical, our attempts to view the beginning of the universe, the cosmic background radiation. There's not so much I know about that, but I can talk about what I know. And all of these are ultimately going to serve towards the main goal of answering questions about habitability. Right now the Earth is the only habitable planet we know of. It's a goal to know more, and it lies at the intersection of all these other NASA fields of inquiry. So the heliosphere around the star exerts pressure on the interstellar medium, the sun, by all the particles, and it's the magnetic fields those particles create. The heliosphere is an astrosphere. Every star that's in the main sequence and committing fusion has an astrosphere. But from where we are, it's hard to see very many of them. We don't have a very convincing or full family portrait of the atmospheres, of the astrospheres, because we can't really see very many of them. And Voyager 1 and Voyager 2 are starting to tell us some things that are unexpected and interesting about our astrosphere, but they were not really instrumented to do that kind of research, to look for that kind of data. We would like to get a spacecraft out there that is really instrumented to answer these questions, that can really pay attention to the magnetic field, different kinds of particles in the interstellar medium. I feel like there was more to say in this slide. My excitement has exceeded my my memory, so let's move on. But the one thing I wanted to say is the sun's astrosphere is the only one we'll really have this chance to investigate in any reasonable period of time. Like, this is our chance. Science goal 2, the formation and evolution of planetary systems. So all of these things, the outer planets, the Kuiper belt objects, the debris disks, are all clues to how our solar system was formed. And we're just now getting the capability to visit those objects and learn substantial things about them. You know, we have lots of models for how this works, and we have some very few observations of other stellar systems that have intact debris disks that we can see a little bit, you know, from a far distance. But again, the sun's debris disk is the only one we can really investigate, you know, firsthand and have any chance of getting sort of in situ measurements, ground truth. And this is going to tell us about other planetary systems and how their planets are formed. And I'm sneaking another little goal in here. Ooh, I didn't even know that animation was there. That's pretty exciting. Exoplanet exploration is a really hot topic now, and there's lots of efforts to try and figure out how to count or see or determine anything about the atmosphere or nature of planets around other stars. It's a really big, exciting question. We're starting to find some answers, but our ability to answer those questions is hampered by our knowledge of our own system. If we could get outside of our own stellar system and look back, we know that there's at least one planet. Well, we think that there's at least one planet in that stellar system, our stellar system, that harbors intelligent life. Like, what could some ET, some witness from outside of our solar system tell, you know, from a distance outside about us and about Earth? We don't know the answer to that question yet. And knowing the answer to that question would tell us a lot that might be helpful in our investigation of exoplanets. Here is that little blue dot, and God bless him, Carl Sagan insisted that they turn the cameras on Voyager around and take a picture of the Earth and other inner planets, you know, at the moment when Voyager was pretty far away. Like, you know, take a look at that dot. That's us. That's our whole planet. Everybody you know or ever knew, every place you've ever been, can't tell much about it from the instrumentation that was on Voyager. So I think it's important to try and get a spacecraft out there with modern instruments and see what it could teach us about exoplanets. So that's my sort of ulterior science goal, but I'm not the only one who has that goal. And science goal 3 is to uncover some real knowledge about the early galaxy and star formation in our universe. And this chart is really busy, and there's a lot here, more than I want to speak to. But the general notion is, you know, we have what we think are pretty convincing models for, like, the beginning of our universe, the Big Bang and the inflation of the universe, and what happened in that very early time. And, you know, we can learn some of that from the cosmic background radiation that we can see from spacecraft in Earth orbit even. And then, you know, at the later end, you know, we can look out and see, we can see other galaxies. When you look far in the universe, you are actually looking back in time because it takes time for light to travel. So, the farther we look, the later back in the history of our universe we're seeing. And so we know something about, relatively new generations of stars and relatively new galaxies, but there's just a sort of dark ages in between the beginning and the part we're familiar with, where we don't have a lot of real firsthand evidence. And the reason for that is because of this zodiacal cloud around the orbits of the planets in our solar system, and it obscures radiation in a lot of really interesting wavelengths. We just have these tiny windows where we can see out through that cloud, and what it tells us is very tantalizing. But if you got a spacecraft with the right instruments outside of that zodiacal cloud, we would have a huge range of more electromagnetic of the spectrum to make observations in. So that's a little bit a hint at some of the science we could address or answer with Interstellar Probe. Let's see, having problems advancing slides at this point. Let's see. Oh, there's a question. Let me take a question for a second. How consistently or inconsistently crowded or dusty is our solar system, and with what? I don't know so much about that, the answer to that question, but I do know there is an instrument on New Horizons that is trying to sample the dust that it comes in contact with. So that's one example. I'm going to defer a more substantial answer to that question. I might have to bring in other resources. Thank you. Let's see. Let me try to share again. Let's see. Thank you for your patience while I fiddle with Zoom. Let's see. All right. So this slide talks about the trade space that the study is working in. The broad engineering goals we're trying to address. We want the spacecraft to be ready for launch no later than 2030. That's a lot of time from now, it sounds like, but there's a lot of technology and mission development that needs to happen between now and then. The idea is to do the science at range, like out there where the spacecraft goes, and bring that data home to Earth. There are strict limits on the power that this spacecraft can have. It's going to travel with 2 radiothermal electric generators, and over time they have half-lives of their radioactive sources that causes the power to be less over time. So the longevity is a big goal and kind of a difficult one. We want the spacecraft to last no less than 50 years from launch. There are multiple trajectory options under consideration. A passive Jupiter gravity assist, a propulsive Jupiter gravity assist, where we burn a stage at Jupiter to get a boost. And then there's this thing called the solar obirth maneuver, which is pretty exciting. I don't know if I'm gonna have time to get into too much of that. And there are multiple science payloads that we're considering. But the central question of getting Interstellar Probe out there has always been propulsion. And there are lots of great ideas, but to sell this mission and to be responsible for the funds, the public funds that NASA might put towards this mission, we really need to rely on a propulsion that is tested, that is well understood, that is low risk. And so I feel like APL is as good as any other place at this melding of compelling science with believable, plausible, reliable engineering. And this is a philosophy that they followed in Parker Solar Probe. Is there more Q&A coming up here? Yes, we're going to say more about science payloads briefly, but I'm not the best person to ask. Wait, I don't know. I'm having problems advancing slides in this mode. So let me drop out for just a second and try and share this in a different mode. I don't understand why I'm let's see. All right, let's see. Share. Here we go. So this is the slide about mission concepts, and we sort of talked through the first two earlier. The third one is this Jupiter gravity assist with the Oberth maneuver. So Hellman Oberth was a European astrophysicist. He invented this maneuver. It would be a great life goal to have a maneuver named after you. Let's see. The idea of the Oberth maneuver is, here's the you can see it while I talk about it. Here's the Jupiter gravity assist, sends you straight towards the sun, and at the closest approach to the sun, you fire the last stage, and you get this big velocity burst because you're moving really fast when you fire that last stage. For it to work, it works better the closer you get to the sun, which is why no mission has attempted it yet. But it's one of the things on our menu of things to analyze because it does give us a boost in the rocket's acceleration out of the solar system. Let's see. Okay. So where could we go with such a spacecraft under any of those three mission concepts? So here's a projection of the night sky. What you're seeing is light and dark based on these energetic neutral particles, which are one aspect of the interaction between the interstellar wind or the stellar wind and the interstellar medium that was surprising. And a recent mission called IBEX made this map much like orders of magnitude better than anything we had before, but still cruder than we'd like it to be of these energetic neutral particles. And so the nose, the dot here that says nose, is referring to the direction in which the sun is moving through our galaxy. And so these boundaries between the interstellar wind and the stellar wind and the interstellar medium are not perfectly spherical, and they're not conical. They're a much more interesting, unintuitive shape. And so there's this interest in some ranges of the science of going in the direction, and there's some benefits of going in the opposite direction towards the tail. And then also there are these, I don't know where the names went, but each of these, there we go. So here are the outer planets that we could visit. And then here also are a lot of these Kuiper belt objects that we know very little about, that are also clues to the solar system's foundation. We could go to some of them conceivably also. So there's a lot of choices there. This is a great slide, and I spend a lot of time looking at this. I don't want to speak to it too much. That sort of white smear or ribbon that we saw on the previous slide of the energetic neutral particles is also here in this sort of S shape highlighted. And then there's energetic neutral particles in a different band of excitement that are here in this other sort of O shape. But the thing I want you to notice here, the vertical axis is latitude of the Earth, no, of the relative to the solar plane, and the horizontal axis. There's two sets of scales there, but the one I want you to pay attention to is years. So this is marked off with 10 different launch years, and the ovals you see, these different colored ovals are escape velocities for solar system escape velocities based on the trajectory. So there's 1 year where a certain planet may be right in the middle of the fastest possible trajectory available, and then there are other years that are maybe less interesting. So where is this study today? Okay, so we've done some analysis of the trajectories. We've done an analysis of possible classes of payloads. We'll talk a little bit about that soon. We talked a lot about, we investigated different rockets, different collections of stages and boosters, and how that would work with the 3 different mission architectures we contemplated. The baseline mission concept has been developed. In the next year ahead, we'll spend a lot of effort on this Oberth maneuver option. So for the science, like I said, there are a lot of competing priorities and interests. Rather than dictate an answer there, APL has chosen to go with a kind of a menu approach to engage the wider technical science and technical communities, and to assemble a menu of different options for what has been done in the past and what could be done for Interstellar Probe. And then the ordering from the menu will be done by a science definition team at NASA's discretion. That wouldn't be our final choice, but whatever, just like when you go to a restaurant, the idea is anything that's on the menu, unless they tell you they're out of the fish or something, you have some confidence. If I order that thing on the menu, I know what I'm getting, and that's the idea here as well. And then I'm not going to talk too much to this slide, which is a set of example payloads. This slide's a little old now. I've actually seen a graph that's much more elaborate about, well, if you want to just do the heliophysics, here's what a suite of instruments might want to look like. If you want to do heliophysics and then some planetary sciences, you pass by Jupiter and maybe perhaps some outer planet, this is what that suite of instruments might look like. So there's been a lot of options there. There's a lot of trade-offs because they're not all equal. They need different kinds of resources on the spacecraft. Some of them need to look in the direction the spacecraft is going. Some need to look perpendicular or back towards the Earth, or in a hemispheric direction. And so there are a lot of trade-offs to consider here. But the basic thing is, you have all these particles, particles from the sun, particles from the interstellar medium, and magnetic fields and electromagnetic radiation. And we want to build a diverse enough suite of instruments to see or record all of the interesting things that we pass by. It's a big topic, and a lot of effort has been invested in sort of delineating what can be done. Oops. Okay. Engineering questions. So there's lots of things here. Again, I feel like we're pressed for time a little bit. There's a question about how the spacecraft moves through space, whether it's a spinner, whether it's if you can change its pointing in 3 different directions, by virtue of the fact that the big radio dish needs to be pointed to Earth, and it's bigger than anything else on the spacecraft. It's not mobile. It's not on a gimbal or something. It's actually welded to the rest of the spacecraft. That determines to some aspect, how the spacecraft will move, will need to move when it sends data home, which is not constantly, it has to share resources on the deep space network that NASA maintains with lots of other ongoing missions. Yeah, so, you know, the other bullet here that I'm excited about is this idea about longevity and fault management and fault tolerance. The spacecraft goes out there, it takes a long time to talk to it, and it's very hard to get too much data from it in a hurry if you think something is amiss. So the spacecraft needs to be very autonomous. It needs to look after its own health and make its own decisions when things start to go wrong. Keep pushing the wrong button here. I'm going to slip through this slide because we talked about some of these things before. This is kind of where we are in terms of engineering choices. Mass is going to be 850 to 950 kilograms. That's a bit more than the curb weight of a 1966 Beetle. That's not a lot considering everything we want the spacecraft to do. The power is going to be 600 watts at the start of the mission, and at the end of the nominal mission, 50 years later, it's pretty predictable. It'll be about 300 watts, worst case, when it gets to 50 years, and that's about 3 bright light bulbs worth of energy. That's not a lot of energy to conduct a space mission. And then the telecom, once it's out there, its bandwidth to send stuff home is going to be very limited. I mean, it's possible, you know, we down here on Earth might build a giant array of antennas and get much better at talking to it, but it's never going to have a better antenna than the one it leaves Earth with, unfortunately. And at 500 bits per second, if it decides to write a science fiction novel like Dune, about the size of Dune, it would take it an hour and a half to download it to us in PDF format. I don't think it's going to do a lot of writing while it's out there, but you know, it's going to have a lot of time on it. And this slide is just to emphasize that there is kind of something like a zero. How do they say it? All of these subsystems are competing for resources on the spacecraft, for weight, for power, for a place on the spacecraft. And it's a very, you know, a delicate bit of engineering to make them all live together happily and communicate and work. Beyond the propulsion systems that are being considered, APL is also researching solar thermal propulsion, which is another old idea that has never been used on an actual NASA mission before, to my knowledge. And it's coming from the technology that was developed from Parker Solar Probe. In Parker Solar Probe, they developed an entirely novel heat shield that needs to face the sun in order to keep the spacecraft working. And the idea was, instead of just passively shielding the spacecraft from the sun, what if we filtered the propellant through that shield and let it absorb the heat? And then the propellant gets hotter and it expands, and that can be a source of propulsion for the spacecraft. And so the numbers I've heard in meetings are something like, you know, 3 times as efficient as normal propulsion. That sounds great. This solar thermal propulsion didn't work or convincingly work on paper before, because you needed to condense a lot of sunlight to get it to happen. Like, you know, the proposed mission elements that use that would have like gigantic reflectors and condensers. It turns out if you move the spacecraft really close to the sun, you don't need all that stuff. So that's the idea here, is if you did one of these birth maneuvers and you got the spacecraft close enough, you know, the sun's power itself would help with the propulsion. This technology may not be ready in time for Interstellar Probe. You know, it's a big trade-off. You know, you bring a lot of other stuff along with you, like this fancy heat shield, heat exchanger thing to do it. So it may not be ready for prime time, but the Applied Physics Lab is making a longer-term commitment to investigating this propulsion method and developing the necessary technology. This is the guts of the spacecraft architecture. I'm the Avionics lead nominally, so this is part of my job too, to figure out how the interior of the spacecraft, all those components talk to each other, how they store data, how the data gets to the radio and gets down, how the power gets sent around, what happens when any of these things stop working. I could talk to this slide for a whole hour and bore anybody who's still listening. But the thing I'm excited about is this galvanic isolation of the space wire bus that's allowing everything to digitally talk to each other inside the spacecraft. So if there's long-term some power accumulation in one component relative to the other, it shouldn't make a difference. I'm glad to take questions about that later. So this slide is very busy. On the left-hand side, it says, what do we know? The heliosphere is more complicated than anybody ever believed, right? It's shaped by the interstellar magnetic field, the pressure of the interstellar medium, and the plasma that's moving through the galaxy. This very complex interaction between the solar wind and the interstellar medium. Our understanding is severely hampered by insufficient knowledge and in situ measurements of the boundary conditions at the edge of what the heliosphere. In situ science is the answer. Do the science there and do the science all along the way there. This is a long run mission. It has multiple phases. We can do compelling science at each step along the way. Ignoring all the words, just look at the picture for a second. I would argue that it's beautiful. It's beautiful and it's our home. Like every living creature that we know about is in there. And this is what protects us and makes life possible. And we don't understand it. And as a species, we are obliged to try to find out. Sorry. Of necessity, just like building the great cathedrals of yore, this is a multi-generational effort. And the top of this graph is what you're familiar with, or somewhat familiar with, the planets, what's outside of the solar system, and what's in this really complex, poorly understood boundary region, all these things that are going on there, the heliopause, well, you can read. But the bottom of this graph is what I want to emphasize to you. There are the scientists and engineers and mission planners and mission operators that will make this work. And they're not all people who were hired previously. They're not all people who were even born yet. We don't even have a name for the generations that are going to come after us that we're going to have to hand off this mission to. And I'm a little unhappy with the graphic because it shows half of these little parabolas, the arcs of people's careers as they enter into this mission and then eventually age out of it. But the point is that these arcs have to overlap. There can't be just some cliff where everybody retires and then somebody new gets the instruction manual and guesses how to make it work. We have to find ways to pass our knowledge from one generation to the other and make the ground system continue to work over all that time. This overlap is essential. Okay, I feel like I'm doing kind of good here. I'm not going to read the Russian. There are members of my family who are really great Russian speakers, and they've all told me, Chris, don't do that. Don't embarrass yourself. But this is a picture of Tsiolkovsky, one of the very early Rocketeers. He was the originator of the rocket equation. And not only was he technically a very brilliant mind, but he was a dreamer too. Just like the people at this science fiction convention, and just like some of the people working at the lab now. And I'm going to read the traditional translation of this quote. Earth is the cradle of humanity, but one cannot live in a cradle forever. I get a little choked up. So Ralph McNutt is one of the people who is the driving forces within the lab for this mission, for this project. And for the life of me, I feel like he said this before, but I can't find the quote anywhere. One day I may call him up and ask him to read it, just so it's official. But I swear I heard him say it somewhere before. The first step of into a new frontier is the most important one. And just like as they built the cathedrals, new technologies happened, new ways of thinking about architecture, new ways of thinking about what a cathedral should be happened, on the course of doing this mission, like doing it responsibly and responsibly and reliably, we're going to learn new things about conducting missions, about the places where the spacecraft is going, about how to make spacecraft, and I think it's better to start doing that now than to wait for conditions to be perfect. And if this excites you to any degree at all, please take the time to find this website and take a look. It honestly doesn't look very great in a cell phone, but if you put it on a laptop, it's kind of beautiful, and it's being updated all the time. It will tell you about, wow, I see a lot of Q&A questions. I kind of want to get to the next couple slides, but let me see what the Q&A says here. How are different than prior missions? How are the instruments different than prior missions? Because from missions like Cassini and IBEX, we know more about the interstellar, the range of the electromagnetic spectrum that is of interest. We know more about the magnetic field that the sun provides for us. I am not an expert on all of the science of the instruments. I will try to find some better answers and post them soon. Ooh, I see some people are answering questions here. Better than I am. Let me step through this for just a second. I'll try to answer some more of these Q&A questions in the chat after the talk, but I see we're getting close on time. If I can just click through a couple more slides, I'll be closer to answering the title of the presentation at least. Let's see. Maybe. Oh, I know. Let's see. So a different mission that's happening at APL right now is DART, NASA's first planetary defense mission. I have flight hardware on that mission. It launches hopefully in July of this year. It is a 2-year mission. If it works, there will be no extended mission because the goal is to crash into an asteroid to demonstrate protecting our planet from a possible asteroid impact. It's the first mission of its kind. There's lots of new technology on there, like this, this really near real-time or real-time guidance, because we're really not going to get a good look at that smaller asteroid Dynamis before the last hour of the mission. There's other technologies on board, a new type of ion engine, these rollout solar panels. When it hits the asteroid, it's going to be moving at 6.6 kilometers or 4.1 miles per second. It should be really exciting. I hope we all get to see it happen. Are you seeing these slides, I wonder? I hope. This just gives you a sense of the size of the asteroid that's the target for this mission relative to some objects you may be familiar with. Another mission happening at the Applied Physics Lab right now is Dragonfly. Dragonfly is a lander for Saturn's moon Titan. It is a rotorcraft, a drone that will fly across the surface of Titan. The idea is that it can do all the surface and atmospheric science. It can particularly investigate complex surface chemistry over varying terrain. It can take, science experiments, the whole chemistry lab, wherever it needs to go to see the most exciting or interesting chemical, pre-biological elements of the landscape there. And even while it's in flight, it can be doing science. It can be giving context to the surface measurements. It can scout new sites of interest. It performs this kind of a hopscotch maneuver where it goes beyond where it's going to land for the day, scouts the next landing site, and then comes back to the site of its next landing and where it's going to do some science. Let's see. I'm sorry, my ability to, let's see. Oh, here we go. One more slide. And this is why this is exciting to me, because Saturn's moon Titan has a complex methane cycle, and it's similar to Earth's water cycle. There are open bodies of liquid on the surface of the planet, lakes, there are clouds, there's methane rain, there are flowing liquids on the surface, things like rivers. There's all this complex organic material being generated by those mechanisms. It's abundant, it's varied, it's easily accessible. It's on the surface of the planet. If you could just get there and move your probe around, you could do a lot of science in a big hurry. And this planet has a very thick atmosphere, low gravity. It makes it an excellent place to be a rotorcraft or to have a rotorcraft. I don't know if this is true. This is really anecdotal, but somebody told me if I had 2 good stiff pizza boxes and I was on the surface of Titan, I could fly. That's the difference between Titan's atmosphere and gravity and Earth's. And this little insect picture here is Titan. It was taken from Cassini, and the glint is sunlight off one of these mares, these bodies of liquid methane and chemicals on the surface. How are we doing time-wise? I'm probably way over.
Yeah, I'm afraid we're out of time.
Okay. So I'm going to hop over to Discord and try and answer questions and chat with people as long as I can make coherent speech. And I welcome folks who want to follow me there. I'm excited that people have questions. And I'm excited that people are giving good answers in my absence. Thank you, whoever did that. Okay. Thank you so much for everybody who came and attended today. And I hope you'll follow along because hopefully this isn't the end of the story. Have a good Balticon, everybody.